Today, we're going to talk about something called cluster analysis. So, what is it? Well, it's basically the science of teaching a machine to find hidden groups in a huge sea of data totally on its own. Let's get into it. At its core, clustering is something we all do, like all the time. It's totally instinctive. From the time we're kids, we're sorting the world into categories just to make sense of it all. It's a fundamental part of how we learn and see patterns. I mean, just think about it. When you do your laundry, right? You don't just chuck everything in the washer at once. Of course not. You create little groups, darks, lights, delicates, all based on what they have in common. Guess what? That's clustering.
Or what about your favorite streaming service? It doesn't just throw a random massive list of every song ever made at you. No way. It organizes them into these neat little clusters we call genres. 80s rock or chill lo-fi beats. It's all to help you find what you're looking for.
And this instinct, it goes way beyond our daily lives. I'm talking cosmic scale. Scientists, like astronomers, they classify entire galaxies into groups, spiral, elliptical, irregular. And they do this to understand the very structure of our universe. See, we are all natural-born clusterers. Okay, so that's all well and good for us humans. But here's the real challenge, and it's what we're really digging into today. How in the world do you translate that human intuition, that gut feeling, into a set of instructions a computer can actually follow? How does a machine learn to see the patterns that just seem so obvious to us? So, to answer that, we first have to tackle a surprisingly tricky question. Yeah, before we can even find a cluster, we have to agree on what a cluster is. Okay, so here's the textbook definition. The goal is to group things so that the stuff inside one group is super similar, and each group is super different from all the other groups. Sounds pretty straightforward, right? Well, not quite. And this brings us to the big, kind of surprising secret of cluster analysis. Get this. There is no single, universally agreed upon definition of a cluster. It's a fuzzy concept. And that fuzziness is exactly why there are so many different algorithms out there trying to find them. Yeah, because the definition is so flexible. Different algorithms are basically looking for different kinds of shapes. Some of them define a cluster as a bunch of points all huddled around a central average, like a swarm of bees around a hive. Others see it more like a dense, crowded neighborhood of data points. And then you have others that connect the dots between close neighbors, or they look for groups that fit a perfect statistical pattern, like a bell curve. Okay, to make this really concrete, let's compare two really popular algorithms that have completely different ideas about what a cluster even looks like. This is going to perfectly show why that definition we talked about matters so much. All right, first up, we've got one of the most famous algorithms out there called k-means. It's a classic example of what's called centroid-based clustering. Basically, it thinks of clusters as being like nice, round spheres, and each one has its own center of gravity. The way it works is actually this really elegant little dance. First, you just drop a specific number of centers, let's say 3, randomly into your data. Then, step 2, every single data point gets assigned to whichever center is closest to it. Step 3, you move each center to the average location of all the points that were just assigned to it. And that's it. You just repeat those last 2 steps, assign points, move the center, assign points, move the center, over and over again, until the centers just settle down and stop moving. And boom, the final groups are your clusters. Okay. Now for a totally different philosophy. Meet DBSCAN. This is a density-based algorithm, and it could not care less about centers. All it cares about is how crowded the data is. So DBSCAN's logic is kind of like looking for bustling cities on a map. It just wanders through the data and finds a point. If that point has enough neighbors within a certain distance, it says, aha, this is a dense area, and that's the start of a cluster. Then it just expands outward, connecting all the dense neighbors it can reach. And anything left over, out in the sparse, empty countryside, it just considers that noise. So when you put these two side by side, their worldviews are like night and day. K-means is really rigid. It basically assumes all clusters are these perfect round blobs, and it forces every single point to belong to a group, no exceptions. DBSCAN, on the other hand, is super flexible. It can find clusters of any weird shape you can imagine, like a crescent moon or a long snaking line. And it has the wisdom to know that some points, well, they just don't belong anywhere. They're outliers. And look, this isn't just some abstract theoretical exercise. These different ways of seeing patterns are running silently in the background of dozens of technologies you use every single day. Think about it. Companies use clustering to group you with similar customers for those targeted ads you see.
Recommender systems suggest a new TV show because you've been clustered with people who have similar tastes. It's used to find communities on social media, to identify objects in a photo by grouping pixels that look alike, even to help police identify crime hotspots or help doctors distinguish different types of tissue in medical scans. It's everywhere. And this brings us to probably the most important takeaway of all. Finding clusters isn't some purely automatic mechanical process. It's really an act of exploration that absolutely requires human judgment.
A data scientist can't just press a button and get the answer. Why? Because, as our source material puts it so perfectly, clustering is in the eye of the beholder. The right method depends entirely on the kind of patterns you're looking for and the kind of data you're working with.
Right. An algorithm isn't some magic truth finder. It's more like a lens. Key means gives you a lens that sees round, well-behaved groups. DBSCAN gives you a lens that sees dense, weirdly shaped groups. So choosing the algorithm is really choosing the perspective. And that choice fundamentally shapes the entire story your data ends up telling.
And that leaves us with one last really fascinating question to think about. If there are multiple, equally valid ways to group the very same data, and each one tells a slightly different story, how do we decide which story we should choose to trust?